Welcome to the lecture number 23 of the course Computational Hydraulics. We are in module 2 numerical methods. This unit, unit number 19, will cover this mesh free method, and specific topic is space time moving least squares method. In our previous lecture class, we have discussed only spatial discretization using or single variable discretization using moving least squares. In this particular unit, we will try to introduce the time concept within the discretization framework. Learning objectives. At the end of this particular unit, students will be able to discretize the spatial and temporal derivatives of single valued multidimensional functions using our mesh free approximation. And they will be able to derive the algebraic form using discretized partial differential equation or PD, initial condition and boundary conditions. So, let us consider our general form equation. In this case, we already know that if we have a general variable phi, which is a function of x, y, z and t in our physical system, where x, y, z, these three are space dimension and t is the time dimension. So, first term is temporal derivative, second term is advective term, right hand side first term is your diffusion or diffusive term, and this is other forces, and S phi is our sourcing term. In this case, capital gamma phi and epsilon phi, these are problem dependent parameters, and gamma phi, these are tensors. We already know this from our previous lecture classes, but in this case we need to concentrate on the temporal or space time discretization. In case of our finite difference approximation, we have discretized this temporal derivative using direct approximation. Let us say if we have phi, which is a constant, del phi del t for 3 dimensional case, we can easily discretize by I j k and L plus 1 minus phi I j k L divided by delta t. L and our L plus 1, these are a time index for this particular discretization, where we are considering that phi is a function of x, y, z and t. But the problem is, in this case we are considering two derivatives. If you have one dimensional case, then we have simply x and t in time dimension. Then if this is our time level L, and this is our time level L plus 1, then for any particular space level I, we can calculate this derivative, where del phi by del t equals to our phi I L plus 1 and phi I L, this is divided by del t. When there is increase in the number of dimensions, we are considering 2 points, one at the future time level L plus 1, another one at present time level L. Now, in this case, if we consider the 2 dimensional consideration or discretization, is same thing we are repeating. We are considering that in this case, if we have this as time axis and these two are x and y, this is our time axis. Then for discretization, if this is level L, for any arbitrary point, this one, we can start our discretization, and we will consider one in present, another one in future. So, in finite difference case, we are considering 2 points, one is in present, another one is in future. But the concept of mesh free is such that we need to consider the concept of support domain. Now, whenever we are considering this support domain, we need to specify some radius for that one. So, whenever we are specifying radius for any system, let us say this is one dimensional x and t system. So, if you have different points at different levels, maybe if we move in this direction, there will be increase in t. If we move rightward, obviously there will be increase in x. So, we need to define the radius for radius for this influence domain or support domain. Now, whenever we are considering the central point, maybe this point is our central point. So, if we consider this support domain, we may need to consider multiple points at present and future time level, in this case for calculation of derivatives. So, the concept of mesh free and finite difference is similar, only difference is that we are considering multiple number of points in this case. So, now we can explain the reduced form that we have utilized in our finite difference approximations, where governing equation is for IBBP or initial boundary value problem, where gamma this one this lambda phi is constant, this gamma x, gamma y, these are also constants, and S phi is somewhat specified quantity for any physical problem. Now, with this information we can start our problem, and if we see the initial condition again phi is a function of x y, and at t equals to 0 we need to specify the value of phi, which is phi naught, and it is varying over x and y. And boundary condition, on the left side we have specified boundary, or this is Dirichlet kind of boundary condition d1 d2, and if we have on top, in this case this is Neumann, and in this bottom also we have Neumann kind of boundary condition. Now, we need to discretize these derivatives or equations using our mesh free approximation approach. So, again we can discretize our spatial domain into regular individual points, because these lines or this grid lines are not applicable for our mesh free approximations. We will consider only individual points for our calculation purpose. These points can be either in structured or placed in regular intervals, or they are randomly distributed within this domain. So, we will have number of points within the domain, and certain number of points will be there in the boundary. So, for our governing equation, we need to select the interior points, and for boundary nodes we need to apply our boundary condition. So, this is all about space discretization. Now, we need to consider different levels as we have considered in our finite difference for implicit, explicit and Crank-Nicolson scheme. So, we will have different time slices, and for that we need to consider we will have different time slices here, and there will be another slice on top of this one. Let us say this is another one. So, between these two we need to apply the theory, or maybe there will be inclusion of multiple time slices in a particular calculation. So, it all depends on our temporal influence domain definition. If we define the temporal influence with a higher value, obviously we need to consider multiple time levels. Now, let us define our space time variable. Let us say this capital X, we are defining it with arbitrary spatial position x, y, t. This is applicable for 2 dimensional in space and 1 dimensional in time. one dimensional in time. Let us define a spatiotemporal variable x tilde I, and in this case x tilde represents the difference between this point, this x tilde specifically represents the difference of the spatial position with respect to any arbitrary variable x y z, x y t in this case. So, x minus x I minus x, y I minus y, and t I minus t in this case. So, if we apply it for Taylor series expansion, so obviously for any general variable phi, this can be written where this is our column vector. Now, in this case we can have this is our Jacobian, and this is our Hessian matrix. Now, this phi x I, if we write it as phi x minus our plus x I minus x. So, we can write this next two values, that is x I minus x with this x I tilde, and x I tilde is our increment from x plus this x I tilde. So, let us expand it with respect to x. So, for any arbitrary phi x I, there will be x and del f by del x, del phi by del x, del phi by del y, del phi by del t. So, these three terms will be there, and in Hessian matrix 9 terms will be there to consider the temporal variation. Now, we can utilize this for our calculations. So, in space time polynomial basis, we can write in terms of 1 x I tilde, y I tilde, t I tilde. Obviously, x I tilde individually, this is our x I minus x. Similarly, for other terms, and others are x I square, y I square, t I square, x I y I, y I t I, t I x I. So, these terms will be there. Now, let us define another corresponding vector, that is a vector, which incorporates all derivative terms including Jacobian, our normal function, and Hessian term. So, in Jacobian, obviously mixed derivative, single derivative terms will be there 3. This is our function directly, and this 3 are, or rather this 6 derivatives, individual second order derivatives or mixed second order derivatives, these can be obtained from our Hessian matrix, which is the second order derivative of the function with respect to 3 variables, 2 in space, 1 in time. Now, let us utilize this for construction of mesh free method. Now, phi can be estimated from this one. So, if we multiply this P transpose, this is actually our column vector. So, this is actually column vector. So, P transpose will be a row vector, and individually this will be again a column vector in this case. So, we can get the mixed terms, and we can estimate this phi from this calculation. Now, similar to our moving least squares method, we can define weighted residual, and NS is the number of points in the support domain. It considers both spatial and temporal points at different levels, and this omega, this one considers the weight function. So, we have to calculate the estimated value and the actual value at phi. So, we can get the difference from here. So, if we further write it in terms of our polynomial basis Ax phi xi, and this is our weighting function. Now, let us say this J in matrix form, this can be written with the help of P. Now, we need to construct this P with the help of polynomial basis. A we already know that that is our derivative related function, and phi transpose is again our phi 1 phi 2 to phi ns, number of points will be there. Now, if we consider P, so we need to consider m number of points including the 0. So, 0 plus m. So, 1 m plus 1 number of basis things will be there, and we have n number of points, or in this case, or ns is the total number. So, in this case we can write our P explicitly in terms of that tilde variable, that is x P0 is essentially constant 1, P1 is x naught, P2 will be y naught, P3 will be t naught tilde, like that. Now, we can utilize this for our calculations, and in this case the weight function thing that will be a diagonal matrix. So, in this case we will have this J Ax A Bx phi, where Ax A bx phi we need to calculate, and a and b can be calculated based on p omega and p values, and b again this can be calculated from p transpose this omega x, and further this Ax can be calculated directly from A inverse B from this particular equation or expression. So, minimization condition we need to equate it with a 0, from that we are getting the next level expression which can be further calculated explicitly with the polynomial basis, and Ax A inverse Bx phi this can be calculated with the help of A and B. Now, in this one space time moving least squares method we have expressed our A in terms of A inverse B phi. So, left hand side we have derivative and right hand side we have our defined terms. Now, with the help of this we can get the derivative values. Now, we need to define our weight function. This weight function can be calculated can be calculated from the exponential function. This sigma x, this is our weight function support. So, beyond this support domain this value is 0, otherwise this is continuous within the support domain and it is varying within the support domain. Now, we can further correct the norm. This is directly calculated norm, but the problem is due to the order changes in x and x, y and t, it may create problem in the weight function definition. So, we can scale it with Cx, Cy and Ct values, and we can correct the norm, and we can utilize this particular norm for our weight function calculation. So, we need to consider the influence domain. Let us say we have x t domain where it is one dimensional in space, one dimensional in time. So, if we consider a particular time level which is x t domain, we can see that to calculate that we are considering multiple points. If we move on the leftward side, that is with different space values, change in the space values, rightward side change is only space values, but if we move upward or downward there is change in the time values. So, different time levels are incorporated in this calculation process. Now, we need to define the influence domain for boundary. If we have this x t problem where x is one dimensional and t is one dimensional, then on t axis if some point is there, so nodes involved in approximation will consider like this, and this open circles are unselected nodes. So, this orange color node is our calculation node. Similarly, this is the extreme case where we have a 0 0 point available here, time is starting from 0 and space is also starting from 0. Now, if we have another case where time is 0, but our x is 0, but time is not 0. So, it is on t axis, but we are considering multiple time levels. So, for that calculation we will consider only previous or past time levels and the present time level values, not at the future time level. Now, next level consideration, if you have 0 time level and there is variation in x. So, for a point which is near to boundary or space level and immediate next time level, we need to consider both future and present level time nodes. If you have in between other cases, we can define our node like this triangular kind of configuration may be there for intermediate cases or internal cases. Again this is for one boundary. We can select all boundary points and just immediately next level time values for this calculation. So, you can see that influence domain is important in case of space time moving least squares. We need to define the nodes that we need to consider during our calculation process. So, depending on that there will be change in the size of the matrix. It may be a banded matrix or a skewed one, or it is a full matrix, not a full matrix because multiple number of points will be there which are unselected nodes. So, we need not to consider the influence of those points. So, with this we can start the approximation and we can solve the problem using mesh free. With this lecture we are finishing our discretization process. Now, next lecture onwards we will consider the now our solution process, that is solution of our Ax is equal to or A phi equals to R matrix that we have generated from our finite difference, finite volume and mesh free approximations, and we will try to solve those problems using different numerical algorithms. Thank you.